Okay, good afternoon, everybody. Thank you for coming to this interesting seminar. I will start by showing a short presentation about CMCC. CMCC is the Italian Institute for Climate Change Research, and its mission is to provide reliable, rigorous, and timely scientific results to stimulate sustainable growth, protect the environment, and develop science-driven adaptation and mitigation policies. So CMCC is organized in the form of a network throughout the country. We have 7 sites where there are different divisions. Research divisions, and here are all of them in 7 places. So we have a advanced scientific computing, for example, division in Lecce, and ocean modeling, data simulation, and ocean prediction and application division that look after mainly ocean research issues. And the topics are wide. They range from poverty and migrations to energy and the future Earth issues, as well as to policies, global policy. Okay, so we have different activities, especially at the outreach is done through a communication office. We do, the CMCC participates to many educational programs from high school to the university, and publication and events are the normal ways to disseminate scientific knowledge. So now, short information about question and answer session. Your audio and video is always deactivated by default. If you need to intervene, you should raise your hand. I would prefer you write your question in the question and answer section, so I can answer. Okay, and let me introduce briefly to you, Dr. Just a moment. Yes, Dr. Karina von Schuckmann. Karina is now a senior oceanographer at Mercator Ocean in France, Toulouse. She leads the annual Copernicus Marine Service Ocean State Report, the first European report on climate and extreme events occurring in the global ocean and the European seas. And she got her PhD quite recently at GEOMAR, Kiel, Germany, in physical oceanography. She is a member of many academies and many important groups, scientific groups, the European Academy of Science. She is a member of the Ocean Observation Physics and Climate Panel. And she's lead author of the IPCC AR6 WG1 6th Assessment Report, Working Group 1 6th Assessment Report. So in addition to all these very important reports for policy, she has written also recently this paper that she will talk about on connection between ocean science and policy. So thank you, Karina, for being with us, and I'll give you the floor.
Okay, hello. First of all, I would like to thank you for the invitation and the opportunity to give an overview on some specific results published in different journals and different collaborations, and highlighting the central role of the ocean for the Earth's climate, for society, and also for sustainable development. I'd like to start this presentation with the Earth system view. That is the role of the different Earth system components, and particularly global Earth system cycles, in order to determine the Earth system and Earth's climate. So the global Earth system cycles, such for example, the energy cycle, the water cycle, and the carbon cycle, are the major functioning in order aiming to redistribute, to store and release and to convert energy, water, and also carbon and other substances and traces in between the different Earth system components, like the atmosphere, the land, the cryosphere, and the ocean. And giving the title, my major objective is today to provide you insight on the critical role of the ocean within the cycles, particularly in the heat cycle, and also its particular role for humanity. One of the major impacts we observe today, and which had been assessed, for example, in the IPCC Special Report on Ocean Cryosphere, are the impact of human-induced changes. And I will now provide specific changes observed for the ocean. So particularly see here, within these Earth system cycles, the ocean plays a central role by its through its major characteristic of the capacity to store large amounts of heat and carbon and other substances, but also to redistribute it around distances, around long distances, but also into deeper layers of the global ocean. But there are specific prices we pay for this through the, for example, increase of ocean heat content, so the ocean warming, ocean acidification, and sea level rise, just to name a few. So specifically, as reported in the last IPCC special report on the ocean and cryosphere published last year, the drawback here is on ocean acidification. So again, the ocean has taken up 20 to 30% of global emissions from human activities over the past 3 decades. And the increase in anthropogenic CO2 occurs through the upper 1,000 meter depths, as nicely presented here on the 3D representation for the different ocean basins, as published in chapter 5, with the different penetration depths and reflecting largely differences in the efficiency with which the anthropogenic CO2 is transported from the surface to deeper ocean layers. The consequence we see from this regulating surface of the ocean is that anthropogenic carbon uptake, that the ocean has undergone increasing surface acidification, and the continued carbon uptake by the ocean, which is predicted for 2100, and it's virtually certain to exacerbate ocean acidification. So this here is a presentation on the historical changes and also the projected changes for 2 different scenarios in blue. The low greenhouse gas emission scenario with a high mitigation, so the RCP 2.6, which gives you a 2 in 3 chance of limiting warming below 2 degrees Celsius by 2100, and different temperature thresholds. And in red, the high greenhouse gas emission scenario in the absence of policies to combat climate change, the RCP 8.5, and with temperature rise up to 4.3 degrees Celsius over the next century. So I will continue with these 2 colors, in blue and red, and like to remember these different scenarios values. The other consequence is sea level rise, which is due from the melting of ice, the Greenland ice sheet, Antarctic ice sheet, and the glacier mesolos, and also from ocean warming through thermal expansion. And today there's about 30 to 40% from ocean warming contributing to global mean sea level rise, and the rest is coming from mass changes from ice loss. So during the 20th century, the global mean sea level rose by about 15 centimeters, and sea level is currently rising more than twice as fast. The sea level rise will further accelerate, reaching up to 1.1 meter in 2100 if emissions are not sharply reduced. And the assessment in IPCC rock also showed that there is no scenario that stops sea level rise this century. And we have the choice between below 1 meter and up to several meters of sea level rise by 2300. Ocean warming is another consequence. The ocean takes up about 90% of accumulated heat in the Earth system, and I will further detail this process in upcoming slides. So due to the emission of heat-trapping gases resulting from these activities, the excess heat in the climate system makes climate change irreversible. So as a consequence, the ocean is warming, and it's continuing unabated. Since the last 3 decades, the rate of ocean warming has increased, and around half of the total heat gain in the global ocean has occurred in the Southern Ocean in the last decade. The ocean will continue to warm throughout the 21st century, and by 2100, the ocean will take up 2 to 4 times more heat if global warming is limited to 2 degrees Celsius and up to 5 to 7 times at higher emissions. Specifically, I will provide now further insight into the Earth Energy Imbalance, which is driving or a result of the heat exchange within the Earth system under human-induced changes. And thereby the oceans plays a specific role. So particularly having a light on the energy flow through the climate system from the energy budget. So it's provided that the state and variability and change of Earth's climate are to a large extent driven by the energy transfer between the different components of the Earth system: the atmosphere, the ocean, the land, and the cryosphere. So the energy flows at the clouds, and weather and internal climate modes can temporarily alter the energy balance on various timescales. So as a summary statement is one of the most practical ways to monitor climate change, its variability, and also its change is continually assess the energy, mainly in the form of heat, in the Earth system. Another concept is the concept of the Earth Energy Imbalance. So all energy entering or leaving the Earth's climate system does so in the form of radiation at the top of the atmosphere. And the difference between the incoming solar radiation and the outgoing radiation determines so-called net radiative flux at the top of the atmosphere. So for any climate forcing, if the imbalance is positive, that's meaning that less energy is going out of the systems and coming in at the top of the atmosphere. The energy in the form of heat is accumulated in the Earth system, resulting in global warming, or depending on the climate forcing, cooling, if the Earth's energy imbalance is negative. Today, the Earth system is feeling atmospheric climate forcing. And this is the example which had been published in the 5th IPCC assessment report. It's the energy budget from 1970 to 2011, providing an overview on the cumulative energy flow into the Earth system from different climate forcing and its related climate feedbacks under different climate sensitivity parameters, and providing the insight on the energy accumulation in the Earth system. So today, under anthropogenic climate forcing, the Earth is out of energy balance and directly attributable to increases in carbon dioxide and other greenhouse gases in the atmosphere from human activities, which is leading to heat accumulation in the Earth system and which is driving global warming. So the question arises, and where we had addressed to from a huge group of international experts on climate science, the question is on where does the energy go in the Earth system, and particularly addressing those 4 central Earth system components. So in collaboration with different experts for the climate science for the different Earth system components, we have started to evaluate the heat available to warm the land. And the estimates here are based on previous estimates and updated estimates, and adding new evaluations of different borehole temperature profile measurements providing an estimate of the heat accumulation in the land system starting from the year 1960. A second estimate was a group of atmospheric climate scientists addressing or basing an analysis of the atmospheric heat content based on 3 different global scale atmospheric reanalysis and 2 different observational data sets. One is a multi-satellite data set and another one is on a radio sonde data set, providing also a new and updated estimate of the atmospheric heat content over the year 1980 up to 2018. Another group collaborated here, which addressed the heat available to melt ice. This estimate has been performed for the Arctic sea ice, Antarctic ice sheets, glacier, Greenland ice sheets, and is based on a combined use of in situ and remote sensing observations, reanalysis, ocean reanalysis, and model data under the assumption that the energy uptake by each component is directly proportional to its mass loss. And in this study, the heat uptake over this period is dominated by the mass loss from Arctic sea ice, glaciers, and the Greenland and Antarctic ice sheets. And finally, but not least, the estimate of the ocean heat content for this study. For this purpose, there had been a collaboration established considering 15 different international in situ-based products for ocean subsurface temperature, evaluating the heat content rates for different depth layers from the upper 300, upper 700, upper 2000 meters, and intermediate layer between 700 and 2000 meter depths. What is shown here is an ensemble mean and spread of those different estimates, and the result showed that all in situ-based products show an increase in ocean warming over the past 5 decades at rates of 0.5 and 0.4 watt per meter square for the upper 700 or 2000 meter depths of the near global ocean between 60 south and 60 degrees north. Furthermore, this is the overview on the products which have been used, and all the references provided here can be found in the paper. And the results show, so you see here from the left to the right, dissemination of the different depth layers which have been evaluated for the heat content estimate. And in each of those depth layers shown in different colors, you can see the different time periods over which trend estimates had been obtained for those different heat content integrations. So you can clearly see that with an evolution in time, you have on one hand an increase of ocean heat content, and also for particular on the very right side where you see the 700 to 2000 meter depth layer, the intermediate depth layer, that you can see a propagation of heat into the deeper ocean layers. And in summary from this figure, you can see that over the past decade, between 2010 and 2018, ocean warming rates have reached record levels up to 0.7 and 1.3 for the upper or 700 or upper 2000 meter depths of a near global ocean. So taking all those estimates into account, we have further tackled the question, where does the energy go, in aiming in order to provide an estimate of the global Earth heat inventory. The question before showing you the results is, why should we care about this? So the major consequences of the uptake of heat from this accumulation, anthropogenic heat accumulation in the Earth system, are land warming, atmospheric warming, ice loss, and ocean warming, as just shown you in the time series before. There are a myriad of consequences due to the warming of these different Earth system components. And I will not have the time to directly address, but the overview or extent on how the impacts are and why we should care on how much energy is stored in different Earth system components is already triggered by the fact that there are specific special reports on which had been special and under IPCC, for example, for the land report, for the 1.5 degree report, and for the ocean and cryosphere report. And so the various facets and impacts of observed climate change arise due to the positive Earth Energy Imbalance, which just represents a crucial measure of the rate of climate change. And the Earth's energy imbalance is the portion of the forcing that the Earth has not yet been responded to. And it provides you the information on how much heat is still in the pipeline, how much heat is still accumulated in the Earth system. So in summary, the statement of this international team is that the Earth's energy imbalance is the most critical number of defining the prospects for continued global warming and climate change. So coming now to the Earth's heat inventory performed by the international collaboration we had established in this study, which is published in Earth System Science Data, and also the data are available. So we have used those different estimates for the land, ocean, atmosphere, and cryosphere Earth system components and established the Earth's heat inventory, as you can see here, providing a value of 358 during the period 79 to 2080 zetajoules, sorry. And we could also provide an information on where the heat had been stored. So the majority of this heat is stored in the ocean. For this period, we obtained a value of 89% of heat storage in the ocean, 6% in land, 4% for warming the cryosphere, and 1% for warming the atmosphere. You might imagine that a number like, for example, the 4% appear very small to you, but these 4% are responsible for today's 70% of global mean sea level rise, just to give you an example. We have then derived these estimates from the global Earth heat inventory in order to obtain a measure through the rate of change on the Earth energy imbalance today. And we obtain a long-term value of about 0.5 watt per meter square, and an increased value for the last decade of 0.87 watt per meter square. So just to summarize you the major results of this outcome. So this is an example of where we have, on the one hand, provided visualization on the estimates, which had been provided in different publications over the past years, which are provided here in colors, and you will find the references also in the publication. And in yellow, you will see the estimates we have obtained with our new Earth heat inventory study. And you can see these are the different estimates, one over starting in the 70s, one starting over the altimetry area in the early 90s, and one which is focused on the area where we can see accelerated warming also in the ocean, and starting in 2010. And the major results show that the Earth's energy imbalance continues at a comparable rate as reported in IPCC R5, and that the Earth's energy imbalance is increasing, and compared to the long-term rate, has doubled over the past decade. So the major messages from this study are that, again, during 2010 to 2018, the Earth's energy imbalance amounts to about 0.9 watt per meter square. As stated, for the stabilization of climate, the goal of the universally agreed UNFCCC in '92 and the Paris Agreement in 2015 requires that the Earth's energy imbalance be reduced to approximately 0 to achieve Earth system quasi-equilibrium. And the amount of CO2 in the atmosphere would need to be reduced from 410 ppm to 353 ppm to increase heat radiation to space by 0.87 watt per meter square, bringing Earth back towards energy balance. So we further state again, this simple number, the Earth's energy imbalance, is the most fundamental metric that the scientific community and the public must be aware of as the measure of how well the world is doing in the task of bringing climate change under control. And we call for an implementation of the Earth's energy imbalance into the global stocktake based on best available science. There is a huge recommendation which had been provided by this multidisciplinary climate science community, which has established this study. And we had been about 30 authors for this publication and this work. And so the recommendation is that continued quantification and reduced uncertainties in the Earth's heat inventory can be best achieved through the maintenance of the current global climate observing system, which is very crucial, but also its extension into areas of gaps in the sampling, as well as to establish an international framework for concerted multidisciplinary research of the Earth's heat inventory as presented in this study. Particularly on the gaps, we have provided more details, which I have no time to provide you here, on where the gaps occur and where it would be crucial and further to assure extension of the climate observing system to continually improve our capability on providing estimates of the Earth's heat inventory. Additionally, I would also like to provide you some discussions established on a transdisciplinary approach in collaboration with different experts on the role of the ocean for human systems under anthropogenic changes and for sustainable development. For this purpose, I would like to start with the presentation of the different sustainable development goals, and particularly on the representation of the 3 pillars of sustainable development. The 3 pillars are the environment, society, and economy. This is the vision which had been established by the Stockholm Resilience Centers, and it's a wedding cake presentation of the sustainable development goals, moving away from the current sectoral approach where the social, economy, and ecological development are seen as separate parts. Here, the environment is a fundamental part of society and economy, and all through these 3 pillars are intrinsically linked. This is another representation in order to raise awareness on how critical the ocean's role is in the 3 pillars, the 3 pillars for environment, society, and economy, and thus for the role it can play for achieving a sustainable future. So there are different critical aspects of the ocean, which including services and support and characteristics they provide in order to support the SDG framework, which include, for example, in the environmental part, and as presented earlier, are its capacity to uptake, capacity to take up heat and storage, and also to move it around a large distances and into deeper layers. The ocean is not an oxygen reservoir for life in the ocean. It's an important reservoir for freshwater and for biodiversity. Sea level is a very critical aspect for humanity and or coastal protection. For example, I will provide a specific example later. Ocean space, the Earth system in general, as introduced through the critical role of the ocean in the Earth system cycles, also within climate, but also for weather and extremes, for food security, adaptation, mitigation, for urban and regional planning, disaster risk management, environmental protection, public health and recreation, marine pollution and waste dumping ground, ocean governance and legal frameworks for the so-called sustainable blue economy, and for trade and shipping. This is a representation of the UN 2030 Agenda Sustainable Development Goals, in which the SDG 14, the SDG dedicated to the ocean, is in the center of the SDGs. The message here is that all SDGs are interconnected, and the SDG 14 supports the UN 2030 Agenda and the SDGs as a whole. So the ocean, as shown in my presentation or visual before, it offers opportunity to face causes and consequences of climate change globally, but also regionally and locally, calling for a dramatic scaling up of efforts towards ambitious mitigation and adaptation. The major message here from this study is that a holistic approach that embraces sustainable ocean stewardship informed by science, data, and services to support society and the economy is required to create the future we want. This is a light motto which had been established by the UN Decade of Ocean Science, and is the UN Decade of Ocean Science for Sustainable Development, which is an essential foundation to achieve this objective. We also draw in this paper a discussion on the upcoming so-called Ocean Climate Nexus. On the left side, you have here a general overview on how data science and services can be connected to sustainable development, convention, governance, agreements, and treaties, and different political tools which are shown in the center of this figure. And on the right side, you can see different activities which are going on. I also invite you, if you are confused with all those acronyms, we have provided a table in our paper as well. So the Ocean Climate Nexus is a complex web with diverse opportunities, contradictions, mandates, and goals in the science policy oceanscape. So the 21 to 2030 UN Decade of Ocean Science for Sustainable Development aspires to overcome the challenges to create a more holistic and integrated approach to managing the shared ocean resources of the blue planet, anchored by decades of long efforts. Another point I wanted to raise here is a summary, which is from the Summary for Policymakers of the IPCC Special Report on Ocean and Cryosphere, which is providing a synthesis on the impacts and risks to ocean ecosystems from climate change. You can see here the impacts going from white colors undetectable up to purple colors on very high risks and impacts, and are addressed to different ecosystem components like warm water corals, kelp forests, seagrass meadows, epipelagic, rocky shores, etc., and provides an overview that with increasing global mean surface temperatures, the risks and impacts to ocean ecosystems are increasing. And in many areas, we would expect a very high impact and high impacts and risk on ocean ecosystems. Another representation in order to establish the linkage in this discussion between the importance of ocean science, data, and services are the tool, or let's say the way on how risks from climate change related effects have been addressed. There are three major aspects. So the environmental hazards triggered by climate change, the exposure of humans, infrastructures, and ecosystems to those hazards, and the system's vulnerability. Also, this figure had been provided in the IPCC SROC. And in order to assess all those information, in order to critically assess the risk from climate change, science, data, and service are very fundamental. Science, data, and services are important to understand hazards, to further underline and understand vulnerability, and also to assess the exposure. So policy, management, and governance instruments require sustainable ocean stewardship informed by best available ocean science, data, and services. I raised a question here on how can we achieve knowledge transfer across the pillars interfaces. Again, the three pillars are those pillars for sustainable development, the environment, society, and economy, which are highlighted here in the blue, yellow, and green colors. And this is represented here on how we can move from raw data products interwoven with knowledge, science knowledge, and technical knowledge in order to achieve valuable information and support for users and also for decision making. So this is the so-called added value chain. It's one of the concepts you can use in order to raise a discussion on this importance of adding value to the information. And this is going up from the raw data, interwoven with information up to oceanographic science knowledge, products, and then ocean monitoring indicators and ocean reporting, which are then valuable information for agencies, reporting bodies, and various users. So the added value chain is the core of ocean and climate services. It connects raw products and oceanographic science knowledge to high quality data products and indicators. And these added value products can provide the evidence basis for agencies and reporting bodies, decision makers, other stakeholders, and the public, yielding societal and economic benefit. I give you one example. One example is the reporting activity at the Copernicus Marine Service. So this reporting activity is distinguished in three different tools. One tool is the Ocean State Report. It's a report which is established by a large number of scientists, which for the last report, we had been more than 115 European scientists would have worked and provided different topics on the ocean environment. And we are about to work on the fifth report. It's an annual publication and is going through peer review. Based on this information, there's an establishment in collaboration with communication experts on this ocean state report with a summary for policymakers. And the third tool is the so-called the ocean monitoring indicators, which provides a synthesized information on some specific indicators for the changes in the environment and with the dissemination of numerical values. This is another example of this activity. This is the example of one page we provide here for the summary for policymakers. And I have added here the link in order if you are aiming to explore more this information. There are two examples I also wanted to highlight. One example is this example which is directly linked to the societal pillar of sustainable development and in linkage with information from the environment. So this is an information on sea level rise. This is a figure you have already seen at the beginning of my presentation. And the linkage here is the coastal megacities, which are at risk from rising sea levels. Below here is a figure from the IPCC SROC in 2019, assessing the risk in 2,100 under different sea level rise and response scenarios. And this had been done for resource-rich coastal cities, large tropical agriculture deltas, Arctic communities, and urban atoll islands. And you can see that with an increasing, and particular with the high emission scenarios, again, the colors which I have introduced at the beginning in red and in blue, show you the level of risks which can reach from moderate up to very high. And to meet the challenge of rising seas, robust urban planning requires an understanding of how urban expansion is impacted by climate change, sea level rise and changing boundaries, extending from urban to rural and from river, delta, coastal zones and territorial seas to the open ocean, based on best available science, data and services. And my last example is here an example on which is addressing the two pillars, society and economy. And it's providing an example on how the combined use of environmental essential variables can support a holistic ecosystem approach to substantially improve fisheries management and to support the development of sustainable fisheries. This is highlighted here in this example where environmental key variables like salinity, temperature, oxygen, chlorophyll, and pH can be used to inform the sustainable stewardship required to meet the SDG targets. So sustainable fisheries will support a sustainable blue economy that simultaneously embraces environmental stewardship to support society and a sustainable blue economy. So these are very short, some take-home messages for the ocean, which are very short, snappy, and I have provided more information in my slides. So my 4 key messages for today are: the ocean plays a critical role for Earth climate, its changes and regulation as its critical role within the Earth system cycles. Due to anthropogenic forces, there are unprecedented changes which are observed and assessed in the IPCC and the ocean from human-induced climate change. The ocean provides prospects for continued global warming and climate change and can guide for future action, particularly on its role as a major contributor estimate for the Earth Energy Imbalance. And the ocean plays a central role for sustainable development in the 3 pillars for environment, society, and economy. And to close this presentation, I just wanted to provide you a short snap on a recently published report from the UNESCO IOC, the Global Ocean Science Report 2020, which is providing an overview on the percentage of women contribution, female contribution. On the left-hand side, you can see the ocean science personnel and female ocean researchers in the year 2017. And on the right-hand side, the proportion of female and male participants at international scientific conferences from 2015 to 2018. And the major message of this report is that gender equality in ocean science is the critical having achieved, but challenges to reach it is realistic. So let's continue this way. Thank you very much. And if you have any questions, please go on.
Yeah, thank you very much, Karina. Very interesting. We have several questions here in the chat, so I'll try to answer some of them. I'm trying to ask you a little bit of a synthesis of some of them. Some of them are pointing out to what do we know about what the coastal ocean does in the global energy cycle or the heat, Earth heat inventory. Do we know that?
So yes and no. So the direct coastal information we do not know. We do not have this estimate, and it's particularly the case because of a lack of data for this. Then secondly, there had been some studies, for example, again, coming back to the ocean roll. So I discuss this now for the ocean roll because it's giving up the majority, 90%. And there had been a study that because of the data gaps in the observations of about in the low-lying areas, we can have an impact of about 10% on the trend estimate. So it's about, let's say, 0.1 per watt per meter square, which could impact, but this could have is not yet quantified. It could have just shown that this will impact by 10%. We had also started in this paper discussion also on the Arctic area, so this is another gap. So, so this is my reply.
Okay, thank you very much. Then we have another interesting question here. It says, if you mention, okay, which consequences could have the climate change for the capacity of the oceans to produce oxygen, half of our oxygen? And could there be also an influence of the increasing quantity of microplastic of the different services of the ocean?
Yes, so two replies here. So the first reply is that the information needs to be clear that there is a large amount of oxygen in the ocean, but it's the amount of oxygen which is used in order to make the ocean full of life. And we see there was in the assessment of the last IPCC report, there was a clear indication that there is a decrease, so in deoxygenation of the ocean. The linkage to plastic and oxygen, I think this can be not that right established, but plastic is a pollution and it has harmful impacts on the ecosystems and is another additional threat to the deoxygenation of the ocean on the ocean ecosystems.
Okay, thank you so much. We also have another question about atmospheric pollution. Is atmospheric pollution have a serious impact on the functioning of the ocean?
So if you include atmospheric pollution as one part of the greenhouse gases, I say directly yes. So this is the core of my presentation, because of the atmospheric pollution, if you link to greenhouse gases, this is why we have an Earth energy imbalance. So why the Earth is out of balance. And because the Earth is out of balance, we have ocean warming, and we have also atmospheric warming, and we have cryosphere warming. So otherwise you need more precise your question.
Okay. I think this is good enough. And then another question is, how can we, I mean, what is the uncertainty associated with the coarse resolution of our models and our estimates, since we don't have sub-mesoscale resolving models in climate change scenarios?
Yes, so so this is a very specific question. So I think that, and I'm sure there are publications and work where I'm also implemented and where there is a more rigorous, let's say, in-depth estimation on the uncertainties. So the uncertainties taken into account within this different study is a mixture of the data processing error, and also take into account the gaps, the data gaps, because you start to create the different products based on a gappy basis, and so you make a lot of assumptions. So in the case, if we say we have used an in situ based products, these are a lot of statistical assumptions, and those processing errors have to be taken into account. Okay. However, for your question on the mesoscale variability and the global scale estimate, there is a specific study from a group, and if you want to send me an email, I can send you, the person who has asked the question, I can send you. It's a so-called study on the intrinsic variability, where we could see that for the global mean ocean heat content, there is not much impact on average, but this is completely different at large scale and also at regional scale. So, but I can further provide this person the presentation, the linkage to these research studies.
Very nice. I have another very interesting question here. Does human infrastructure, heat building, managed land, play any role in heat storage by the ocean?
Sure. I mean, I don't have the percentages here, so I know that those percentages are both shown, one in the SROC, but also in this special report on land. And there's also a short assessment in the 1.5 degrees on this different contribution. It's one of the components which is called under our anthropogenic forcing. So this is specifically, maybe we can see it a bit also on the other figure, I don't know. But yes, of course, it's one part of our anthropogenic climate forcing we have. But I don't have the percentage here at hand. Okay. But it's a large amount.
So you're saying that we can estimate that yes. The impact.
Yeah, it's estimated as part of the, our anthropogenic climate forcing. It's a forcing Good. Component.
Thank you very much. Almost close to the last one. Another interesting question about how does all this knowledge feed into ocean literacy?
Yes, so ocean literacy. So I think there are several angles on how this research community is aiming to work on this, and ocean literacy is also one of the key objectives stated by the UN Decade for Ocean Science in order to further advance on ocean literacy. So there's of course this activity at IPCC, which is providing on the one hand these summaries for policymakers, but is also doing a lot of outreach activity in order to change the information into a wider audience, and so to a different audience. We have this also available in the Copernicus Marine Service. There are different countries which have started now to implement also climate change related impacts, so including also the role of the ocean for schools. So, but it's a long way to go, and I think we need all to work together to this. And I think that there are a lot of progress will be done, particularly under the UN Decade of Ocean Science for Sustainable Development.
Okay, now we see the last one here. Can you give an estimation of the increase of heavy storms, hurricanes on the western coast of Europe? I mean, what is the world here?
So I'm not an expert, and I would like to summarize what has been assessed in SROC. It is that there is, in terms of extreme events, there is an estimating that there will be more frequent and more intense events. This has been done, for example, for marine heat waves, and there was also an assessment on the other report on this. But a specific prediction on specifically how much storms, I think this will be not. This is not available, and but there's also much more studies which need to be done in order to further assure the importance of ocean information to improve the prediction of mid-latitude storms. And just recently, for example, there was a very strong tropical storm going over the Pacific Islands just yesterday. So the ocean, adding the ocean into these forecasting systems would improve the forecasting much better. It's information I can provide.
Very nice, thank you. We agree deeply on that. Thank you very much. So I think it is time to close, and thank Karina for this very nice and holistic view of climate in society. And we will invite you soon to the next series when we can discuss more on other technical details or scientific more details of this adventure that we are undertaking. Science addressing policies and helping policy. That's a very important topic. And that you have a last word to give us, a last recommendation. What shall we do in addition to what we do?
Yes, I mean, everybody should take its responsibility. Everybody should also, particularly for the question on literacy, on environmental literacy. So everybody should communicate the information and further raise awareness. But the good news are, for example, that for the first time at the UNFCCC level, there was an ocean distinct related negotiation process going on. So this took place at early December. So for the first time, an ocean-related topic had been discussed, and there were a submission of about 30 submissions from different countries on ocean-related topics. So we are in good advancement, and we have to continue to sustainably live with our environment. So, and if you have any questions, please do not hesitate to contact me.
Thank you again. We had 150 participants and 120 attendees were up to the end. So thank you very much, Karina, again.
Thank you all. Bye-bye.
Bye. Have a good weekend, everybody, and a safe and happy holiday season.